While this might not captivate everyone, the emergence of energy-storing cement composite is groundbreaking. Researchers are developing cement-based materials that act as structural supercapacitors, allowing buildings, foundations, and infrastructure to store small to moderate amounts of electrical energy within the concrete itself. This video explains how concrete energy storage works, who is developing it, how it could connect to solar and wind systems, what it realistically provides, its advantages and limitations, and when it may become practical for real-world use. Before we get started, please consider hitting the like button and subscribing to my channel. It only takes a second, and it really helps support my work. Thanks for watching. Okay, let's get started. Concrete energy storage does not behave like a conventional battery. Instead, systems such as MIT's electron-conducting carbon concrete, often called EC3, function as supercapacitors. These materials combine cement with conductive carbon networks and an electrolyte, allowing electrical charge to be stored across large internal surfaces within the concrete. The result is a structural material that can store and release energy quickly, but at much lower energy density than lithium-ion batteries. This approach is not meant to replace compact high-energy batteries. Its strength lies in integrating energy storage into structures that already require large volumes of concrete, such as basements, foundations, walls, bridges, and other infrastructure. Several research groups around the world are actively working on cement-based energy storage. MIT is currently leading much of the recent progress through work by researchers such as Masik, and Yang Horn, who are developing electron-conducting carbon concrete with improved performance and scalability. Chalmers University of Technology in Sweden demonstrated earlier versions of cement-based rechargeable systems using carbon fiber meshes and metal-coated electrodes. In parallel, academic teams across Europe, China, and the United States are publishing research on cement-based batteries and supercapacitors as part of a broader push towards structural energy storage. While the designs vary, the shared goal is the same: turning structural concrete into a multifunctional material that can support loads while also storing electrical energy. Concrete-based systems like EC3 produce direct current, just like batteries and supercapacitors. Each concrete unit behaves as a low-voltage supercapacitor module formed by two conductive concrete electrodes separated by an electrolyte. Individual cells generate relatively low voltages, so many units must be connected in series and parallel to reach useful levels for real applications. In research demonstrations, series-connected concrete modules have powered LEDs and small test loads, reaching voltages on the order of several volts per assembled stack. To achieve voltages suitable for buildings, such as 48 volts or higher DC bus levels, larger arrays of concrete elements would be required, similar in concept to how conventional supercapacitor banks are assembled today. In principle, concrete energy storage systems can work with solar panels and wind turbines because they output DC electricity. In practice, they are not drop-in replacements for today's home battery systems. Supercapacitors behave differently from lithium-ion batteries, especially in how their voltage changes during charge and discharge. Real buildings would require customized power electronics. A concrete supercapacitor bank would likely feed into a DC to DC converter that stabilizes voltage and manages charging behavior. From there, a standard DC to AC inverter could supply power to a building or connect to the grid. Whether existing solar inverters could be reused depends on voltage ranges, how quickly voltage drops under load, and whether an intermediate DC regulation stage is added. Overall, the balance of system would look familiar to today's solar plus storage setups, but the front-end electronics would be specifically designed for cement-based supercapacitors. Research into cement-based electrochemical systems began in earnest during the 2010s. By around 2021, early rechargeable cement-based batteries achieved energy densities of roughly 0.8 watt-hours per liter. MIT's EC3 work, first highlighted in 2023, shifted focus toward supercapacitor-style designs optimized for structural use. A follow-up reported in 2025 demonstrated roughly a tenfold increase in energy storage through improved materials and processing. Early design suggested that storing around 10 kilowatt-hours of energy would require on the order of tens of cubic meters of concrete, roughly equivalent to an entire basement. With recent improvements, that same daily household energy could potentially be stored in a few cubic meters, comparable to a thick basement wall. While still bulky compared to traditional batteries, this becomes reasonable when the concrete is already needed for structural reasons. Cracking is a natural concern for any concrete-based technology. Minor cracks that do not significantly disrupt the internal conductive network may have a limited impact on electrical performance. Larger cracks, however, could isolate sections of the material and reduce storage capacity. Repairing such damage would likely require specialized cementitious materials that restore both mechanical strength and electrical conductivity, potentially along with renewed electrolyte pathways. To address these issues, researchers anticipate combining conductive concrete with established self-healing strategies, such as mineral admixtures or micro-encapsulated healing agents. Because conductive concrete is also electrically sensitive to strain, it can double as a self-sensing material for structural health monitoring, allowing engineers to detect damage early and manage long-term performance. Concrete energy storage offers several compelling advantages. It uses abundant, relatively low-cost materials like cement, water, carbon additives, and common electrolytes. By serving as both structure and energy storage, it reduces the need for separate battery installations and can save space. As a supercapacitor, it supports fast charging, rapid discharge, and extremely long cycle life, with lower risks of thermal runaway than high-energy battery chemistries. It also aligns well with sustainability goals by enabling buildings and infrastructure to store locally generated renewable energy. At the same time, the limitations are significant. Energy density remains far below that of lithium-ion batteries, making concrete storage unsuitable for space-constrained applications such as vehicles. Large volumes and substantial weight are unavoidable, restricting practicality to structures that already require concrete. Long-term durability under real-world conditions, including moisture exposure, freeze-thaw cycles, carbonation, and mechanical loading, is still being studied. Integration into buildings also adds complexity, as electrical systems must meet safety codes while coexisting with structural requirements. Clear cost figures per kilowatt-hour are not yet available, as the technology remains in the research and prototype stage. However, the reliance on commodity materials and conventional concrete mixing methods suggests that, at scale, concrete energy storage could be cost-competitive in certain scenarios. It's especially when compared to building standard concrete structures plus separate battery systems. Quality control, electrolyte management, and electrical integration will add complexity, but they do not fundamentally change construction practices. For now, no commercial building code-approved products exist. Current work focuses on lab specimens, small blocks, and demonstration elements designed to show feasibility rather than market readiness. The most realistic path forward involves pilot projects in research buildings, specialty infrastructure, or off-grid installations in the late 2020s, then followed by gradual adoption in niche commercial applications during the 2030s as standards, durability data, and costs become clearer. Concrete that stores energy is no longer a science fiction idea. As a structural supercapacitor, it offers a practical way to embed low to medium energy storage directly into buildings and infrastructure. While it cannot compete with lithium-ion batteries in energy density, its ability to combine structure, storage, and sensing makes it uniquely suited for foundations, walls, and large concrete elements. With continued research and careful integration, concrete energy storage could become a meaningful part of sustainable buildings and smart infrastructure in the decades ahead. Leave me a comment with your thoughts on this, then check out some of my other videos. Don't forget to hit the like button and subscribe. Thanks again for watching, and we'll see you at the next one.